And now for the change of variables. Let me show you first of all that we actually did this in Math 3a and Math 3b. So if you're going to integrate, let's say from 0 to 4, the square root of 7x plus 1. And then we decide to use u substitution, so let u equal the inside part and take the derivative. So that would be 7 dx. So then we need to find out what dx is equal to. So multiply both sides by 1/7. And if we're going to change to u, then we could also say when x equals 0, you plug that in and u is going to equal 1. When x is equal to 4, substitute that right there, it's going to be 28 plus 1, so then u is 29. So then we can change the variables. Instead of using x, we're going to use u. So it's going to be the integral of the square root of u, just replacing the 7x plus 1. And then dx needs to be replaced with this 1/7 du. And then instead of having the limits from 0 to 4, the new limits are going to be 1 to 29. And then we could go ahead and integrate. Notice that this thing right here, well, when we change to polar form, we have integrate, and then you've got the function, and then you've got an extra r, dr, d theta. Well, this is like a little Math 3a baby version of this. And we'll soon see when you do the change of variables why it is you need to do this, extra r. Now, let's go from Math 3a to Math 3c. So what if you had an integral like this? It's a double integral. Both of them are going to be from 0 to 1. And then what we're supposed to integrate is x minus y times the square root of x plus y. So basically we need to do a u substitution. So you could let u equal what's inside the radical. And then there's a small problem. That is not the same thing. So we need to use a different variable like v equals x minus y. So one thing is, what happens to the limits? These are going from 0 to 1, 0 to 1. So basically that means if you look at the x, y axis, it's going from 0 to 1 on the x-axis, because this part is saying x goes from 0 to 1, y goes from 0 to 1. So in other words, it's this rectangle. So we're integrating over this rectangle in the xy system. Well, when you change it to u and v, what happens to this rectangle? So with x and y, we can make a little table of values and then take the four corners of this box. So that would be 0, 0, and then 1, 0, and then 1, 1, and 0, 1. Then, using this transformation right here, if you plug in the numbers for x and y, then you're going to get the u and the v. So u is always going to be adding the two together. So I'm just going to fill out this u column right here. So for u, you just add them together. So 0 plus 0, 1 plus 0, 1 plus 1, and 0 plus 1. And for v, you need to subtract. So 0 minus 0, 1 minus 0, 1 minus 1, and 0 minus 1. So what does that shape look like? So this is the u and the v axis. And we have 0, 0. We have 1, 1. There's 2, 0. And there's 1, negative 1. So that is still a rectangle, but it got rotated. So basically, if you take this rectangle and then you rotate it so that this point right here ends up right there, that's the shape that we got. That's called a linear transformation. Okay, now the other thing we need to do is we need to find out what dx and dy get replaced with. So how do we replace those? Well, we're going to have to find the dx and the dy. We're going to have to find the derivative of the x and the derivative of the y. So we'll need to solve for x and solve for y. So with this little system of equations, one thing I could do is add the two equations together and the y's will cancel. On this side, it's going to say 2x. And if you add them together, it's going to say u plus v. So in other words, x is equal to u plus v over 2. Now subtract the two equations. So if you have this minus this, the x's will cancel. Y minus this one will actually be 2y. And subtracting means it's going to be u minus v. And then divide by 2. So now we could find the derivative of x, and we could find the derivative of y. But of course, with this being Math 3C, there's not just one derivative of x, because you have to take the derivative with respect to u and the derivative with respect to v. So then we need, for x, take the derivative with respect to u. So v is a constant, so this is going to be a 1 over 2. Take the derivative with respect to v. This will be a constant, so its derivative is 0. This will be 1 over 2. And likewise for the y function, take the derivative with respect to u. So that would be 1 over 2. And then last, the derivative with respect to v. And then that would leave negative 1 over 2. So in Math 3a, we would just find one single dx. Here, we have 4 derivatives to consider. Then, what do we do with those 4 derivatives? You guessed it, a determinant. So this determinant is called the Jacobian. And it's the determinant of these 4 derivatives. So it's going to be a half, a half, a half, and negative 1/2. So when you multiply these guys, that's going to be negative 1/4. And then minus, when you multiply these guys, that's going to be a 1/4. And then 1/4 and 1/4 is a half, so the Jacobian is equal to negative 1/2. And that means that dx dy gets replaced with negative 1/2 du dv. So if you look back at the Math 3a example, the dx got replaced with 1/7 du. Well, sort of similar right here, except it's a dx dy gets replaced with negative 1/2 du dv. Now, what about the limits? Oh, I guess I should go ahead and just set up the integral, and then we'll do the limits. So this is the integral that we're working on. And this is just going to become the v, and this is going to be the square root of the u. So we'll have double integral, and then this just becomes the v, and then it's square root of the u. And then you replace the dx dy with negative 1/2 du dv. All right, not bad. But then, what are the new limits? So remember, I had made this shape a moment ago, and it was a rectangle, but it was going like this. This is the u-axis, this is the v-axis, this is 1, this is 2, this is negative 1, and this is 1. So instead of the limits just being a number, the limits are going to be the sides, and we need to know the equation for the sides. So this is going through 1, 1. That means u and v are equal. So this is the line u equals v. This one has a slope of negative 1, and if you continued it up, it would cross at 2. So this one is the line v equals negative u plus 2. So that's a slope of negative 1, and then it would cross up here at 2. Likewise, this one is v equals u minus 2, and this one is that v equals negative u. Next up, we actually need to divide this into 2 integrals, because if you're covering this whole area of this whole little square, then you would need, basically you break it up into little rectangles, and then you find the area of each rectangle. And for the left half of the picture, the rectangle is going to be going from that function to that function. And then when you move to the right side, this little rectangle is going to be going from that function at the top to that function at the bottom. Okay, had to go get some more paper. All right, now I'm ready. So our double integral, well, for one thing, I'm going to take this negative 1/2 and just factor it out. And like I said, we have to make this into 2 integrals. One is going to be this left side of the graph, and then the right side. And so it's still going to be v times the square root of u, and then either du or dv. So I just automatically wrote down du dv, but you could always switch the order. Now, to determine the order, I know that the second integral, whatever I put last, that's got to be numbers. And the way that I set up this little rectangle, it's going to need to start over here when u is equal to 0, and then it's going to have to move to right here when u equals 1. So I actually should do u last and v first. And the u is going to go from 0 to 1. And then the v, so at the top, v is equal to u. And at the bottom, v is equal to negative u. All right, then add on this side. So again, you could factor out the negative 1/2. It's still going to be v times the square root of u. And I'm still going to go dv du. And for this one, the v is negative u plus 2 on the top and u minus 2 on the bottom. And then the u needs to go from 1 to 2. All right. It's only been a few minutes and we already set up the whole integral. Now we need to actually do the work. So I'm going to do this one, and then if we have time, we'll come back and do this one. But let's just concentrate on this one. So this means integrate with respect to v. So hold this constant, and this will become v squared over 2. And then evaluate that from negative u to positive u. And then later there would be du, and then that would be integrated from 0 to 1, and the negative 1/2 is factored out. Oh, I forgot to write down my square root of u also. So substituting the u in here, that's going to be u squared over 2, and then minus negative u squared over 2, and then it's still times the square root of u du, and then it's integral from 0 to 1 and negative 1/2. And then that is u squared over 2. Once you square that, it's also u squared over 2. Since you're subtracting them, this equals 0. Oh, that didn't take as long as I thought. Okay, then we can move on to this one. So it's going to be negative 1/2, and then again, this part right here is going to be v squared over 2. And then that gets evaluated from u minus 2 to negative u plus 2. And I still need to write down that square root of u in du, and also the integral from 1 to 2. Okay. Since this is a constant, I could just factor that out and make this 1/4. And then we need to substitute this in for the v, so that's going to be negative u plus 2 is squared. And then minus, when you substitute this limit, u minus 2 is squared. And then all of that is still times the square root of u du. So let's see. This thing, I'm just trying to decide if there's any nice, easy algebra that I could do, or do I just need to multiply this out? Yeah, you're right. We should just go ahead and multiply it out. So the first one would be u squared minus, multiply these two and then double it, so minus 4u and then plus 4. And then this is going to be u squared, but with that, it's minus u squared. The middle term would be negative 4u, but with that, it makes it positive 4u. And then when you square that, it's a 4, but with that, it's minus 4. And then it's still times the square root of u du. And then u squared minus u squared cancel. Negative 4 and positive 4u cancel. Negative 4 and positive 4 cancel. That means that this whole part is equal to 0. So that means that the final answer is actually just 0 plus 0 or 0. And now let's take a look at the graph and see why is the answer 0. So this is the function that we started with. We were integrating x minus y times the square root of x plus y. And then if you take a look at that graph, right here is 1. So we were going from 0, 1 on the x-axis to 0, 1 on the y-axis. And if you look at the graph, for one thing, this is positive, and then this is negative. And the graph is symmetric, so this positive part and this negative part canceled each other out. That's why I've got the answer 0. So before we go on to the next example, let's just summarize how this works. So for the change of variables, so you would make a substitution like, let's say that u equals a function of x and y. And then v is some other function of x and y. Then what you need to do is solve for x and y. And then you find the derivative of x with respect to u, the derivative of x with respect to v, the derivative of y with respect to u, and the derivative of y with respect to v. You create a little 2x2 determinant, which is called the Jacobian. So you find that determinant. And then also the original problem, the region that you're integrating over, or the limits, might be some shape like this. Previously, the one that I did first, that was a nice rectangle. Usually there's not going to be too complicated at this point. And then, because you've changed variables, you then need to find out, well, in the UV system, what happens to that shape? So it now is over here. So you need to find out the new limits. And then the original integral, let's say this is region R, and then this is called the transformation as you're transforming from this region to that region. So then this is called R after the transformation. So integrating the original problem, and then it had something dx dy. So then that becomes integral. So then you would replace with the u and the v, whatever this function was, and then you'd need to put the Jacobian times du dv, and whatever the new limits are, you need to put those over here. Now for the next example, we're just going to do the limits part. So for example number 2, so let's say that the region is u and v, so that u is between 0 and 2, v is between 0 and 1. Now this is a little bit backwards because you usually start with x and y and then you change it to u and v. But if it's a transformation, you should be able to transform back and forth between the two. Just like with integrating, we can integrate with respect to x and y, or we could change it to polar. And if you have polar, you could change it back to x and y. Then let x equal v and y is equal to u times 1 plus v squared. So to begin with, in the u and the v system, so this is like the x and this is like the y, the u goes first, so that goes here. That's going from 0 to 2. And the v is going from 0 to 1. And so that makes a little rectangular box just like this. So this is the line u equals 2. This is the line v equals 1. This is the line v equals 0. And this is the line u equals 0. So what happens to these 4 lines or 4 line segments if you have this transformation? So just previously I said we have a transformation t. Well, this is the transformation t. So you're transforming between x's and y's to u's and v's, or from u's and v's to x's and y's. So let's take one piece at a time. How about v equals 0? So in other words, what happens to this line segment right here? So if v is equal to 0, you can plug that in right there. I forgot to write down v equals 0. You could plug that in right there, and it's going to say y is equal to just u times 1. And x, if you plug in that v is 0, it's this. So then, what does that look like? So now this is the xy system. So that's saying x is equal to 0 and y is equal to u. And u ranges from 0 to 2. So that means it is this line segment right here. So basically it took this shape and it stood it up like this. So this is going to 2. Now, how about the top shape? V equals 1. So substitute in that, and it's going to say x is equal to 1. And if you substitute a 1 right here, this is going to be a grand total of 2. That means that y is equal to 2 times u. So in the xy system, that means you go out to where x equals 1, and then y is going to go twice as far as u did. Well, u used to range between 0 and 2, so if you double that, it's going to go from 0 to 4. So then that is a line segment that is now going up to 4. Okay, now pick another side. Like, how about u equals 0? So what happens to this side right here? So if u is equal to 0, this is going to be 0 times something, so that's 0. And then it's just going to say x equals v and y equals 0. Well, y equals 0, that's like the x-axis. And then this is going to go as far as v does. So it's going to range between 0 and 1. So that's going to be right here on the x-axis, and it will go out to 1. And then once we're done with the 4 sides of this, we'll get 4 pieces, and then we'll put those pieces together. So we've just got 1 more to go. Who's missing? U equals 2. We're missing that one. So if u equals 2, then x is still going to equal v, and y is going to equal, u is a 2, so it's going to be 2 times 1 plus v squared. So then, in order to see what this looks like, because x equals v, I could just plug that in right here. So in other words, y equals 2 times 1 plus x squared. And that's a parabola. And the v ranges between 0 and 1. So that means this v, or this x, ranges from 0 to 1. Well, if x is a 0, then y is going to equal 2. And then this would be a parabola that's going up. So it's going to be a parabola going up like this. And by the time x equals 1, this would be 1 plus 1. So that's 2 times 2 is 4. So it's going to go up to 4. I meant to make this one in red so it matched the others, but that's okay. So finally, put the pieces together. So the bottom part goes from 0 to 1. The right side goes from where x equals 1, and then it goes up to 4. This is a parabola piece, which starts right here at 2, and then goes up to 4. And then this side is on the y-axis, and it goes from the bottom up to 2. So there we go. This is the original region, and then it got transformed into this region. Now, yes, there's more. I know you're excited. For the next example, which I believe it feels like number 13, but it's actually only number 3. Suppose that you made this substitution. You decided, I'm going to do this substitution that x is equal to r times cosine theta, and y is equal to r times sine of theta. Which, if you look at basic trigonometry, that means just set up a little right triangle, find out what cosine equals. So this is just the basic definition of sine and cosine. So what if that was your substitution? So instead of u and v, we're using r and theta. But the idea is the same. We need to find the Jacobian. So take the derivative with respect to r, and then that's going to be just cosine. And then take the derivative with respect to theta, working on the x, and then that's going to be, derivative cosine is negative, so negative r sine of theta. Now for the y function. Take the derivative with respect to r, and that will equal just sine of theta. And then for the y function, take the derivative with respect to theta, and that's going to be r times cosine of theta. And then find the Jacobian. So make a 2 by 2 determinant of cosine theta, negative r sine theta, also sine theta, and positive r cosine theta. So what does that equal? Multiplying this diagonal, that's going to be r times cosine squared. Then minus, when you have this diagonal, well, this diagonal is going to be minus r sine squared. You get where I'm going with this? Then you could factor out r, and it would leave cosine squared plus sine squared. And since cosine squared plus sine squared equals 1, that means the Jacobian equals r. Which means that if you had some double integral that had something dx dy, then when you change over to the system that has r, and when it has r and theta, then it would be double integral. You would replace the function. You'd have to multiply by the Jacobian, and then you have to put dr and d theta. So that is the reason that we have to put this extra r every time we do the polar integration. And now for example number 4. Suppose that you've got this double integral over a region, and we're supposed to integrate x squared dA. So in other words, this could be dx dy or dy dx. And the region R is bound by 9x squared plus 4y squared equals 36. Well, notice that this is an ellipse, and it would have been so much easier if it was a circle. Because if it was a circle, even if it said 9x squared plus 9y squared, you could factor out the 9, and once you have x squared plus y squared, you change that to r squared, you change it to polar, and we'll be done in about 2 minutes. But with an ellipse, that makes it more challenging. So, is it possible that you could use a transformation where the original picture is an ellipse, and then you change it to a circle? Well, let's try it. So use this substitution. Let x equal 2u, and let y equal 3v. So we do need to find the Jacobian. So for the x, take the derivative with respect to u. That's going to be 2. For x, take the derivative with respect to v, that would be 0. For y, take the derivative with respect to u, that would be 0. And for y, take the derivative with respect to u, which is going to be 3. So that means that the Jacobian is going to be this 2 by 2 determinant. 2, 0, 0, 3. So the Jacobian equals 6. Now what happens to the boundary? So directly just make the substitution. So it's going to be 9, and then x gets replaced with 2u, that gets squared, plus 4, and then y gets replaced with 3v, and then that gets squared, and it equals 36. So this would be 4u squared times 9 makes it 36u squared. This would be 9v squared. 9 times 4 is 36. V squared equals 36. Then divide everything by 36 and you're left with just u squared plus v squared equals 1. And this is a circle with a radius of 1. So that means that once you've got a circle, we can change it to polar, and it would be much easier with polar. Well, let's see. First of all, it's going to be integral, and then x has to be squared. So the x has to be squared, which means this has to be squared. 2u needs to be squared. And then it's times the Jacobian, so times 6, and then du and dv. So that's just the basic substituting these in and the Jacobian. And then with the limits, I could solve for v and it would be 1 minus u squared inside of a square root and start putting that as the limits. But it would be easier to change this to polar. All right, in polar it's going to be integrate. This needs to be squared, so that's going to be 4u squared. And then times 6, so that's 4 times 6, that's 24 u squared. Well, to change to polar, I usually, for polar, you go x is equal to r cosine theta, y is equal to r sine theta. Those are two of the formulas that help us change to polar. But in this, instead of x and y, we have u and v. So we're going to use u and v. So u is equal to r cosine theta, and v is equal to r sine theta. Okay, so I established this is 4 times 6 is 24. Then u has to be squared. So u has to be squared. So that means square r and square cosine. And then, because we're changing to polar, we still need the r times dr d theta. Then, what are the limits? Well, we're talking about this circle right here, and it's a circle of radius 1 because of that. So r is going from 0 to 1, and to go all the way around the circle, that goes from 0 to 2 pi. So notice in here, I could put the r's together and put that together with the dr. I could take this that has theta, and I could basically separate this into two integrals that are multiplied together. So one of them will be the theta information. It goes from 0 to 2 pi, and then it would have cosine squared and d theta. And then that is the only theta information. This 24, we could just factor it out. Then multiply with, for the r's, so there's r and r squared, so that's r cubed, dr, and that goes from 0 to 1. So in order to integrate cosine squared, then we need to use the trig identity. Cosine squared is 1 plus cosine of 2 theta over 2. And then for this one, we could go ahead and integrate it. That's going to be r to the 4th over 4. And that gets evaluated from 0 to 1. And then for this one, I would factor out the 1/2, so this actually becomes a 12. And once you do that, the antiderivative of this 1 is theta. The antiderivative of cosine is sine 2 theta. And because of the chain rule, you have to divide by 2. And then that gets evaluated from 0 to 2 pi. And then for this part, substitute the 1, that's going to be 1/4 minus 0 over 4. And we're almost done. So there's a 12. When you substitute the 2 pi for theta, you get 2 pi. When you substitute this, sine of 4 pi is 0. When you substitute a 0, that's 0. And when you substitute a 0 right there, sine of 2 times 0 still equals 0. So all that's left is this single 2 pi right there. And over here, all that's left is a 1/4. Finally, so 4 divides into 12 3 times. And then 3 times 2 pi equals 6 pi. Ta-da!